My name is Kurt Detweiler. I was the lead systems engineer for the Systems Engineering and Integration Organization for Ares 1X that was led out of the NASA Langley Research Center. Responsibilities were just all the cross-cutting discipline type issues, resolving of those and getting those tamed and to help move the project forward. Basically following the original, the initial implementation of Ares 1X, the requirements formulation. After all that was completed, we worked primarily I worked the issue side of things from that occurred through design all the way through flight. Given the fact that the organization, the Ares 1X team, the elements were stood up and proceeding ahead of SE&I, the loads definition was essentially late, and the elements, there's a strong possibility the elements would have to redesign, requal, or have to refabricate as the end result to accommodate that aspect, that lag from SE&I. For a typical project integrated design and analysis cycle, you have typically three design cycles that you go through. One, design cycle 1 typically supports PDR. Design cycle 2 will support CDR, and then there's a design cycle 3 that a lot of the disciplines like to put on the table to capture any loose ends, and essentially they term that a verification cycle, and that's done prior to flight. Design cycle 1 is, from a loads perspective, is typically encompasses or utilizes what's termed quasi-static loads. It doesn't really get into the detailed dynamic loads that you would see in a coupled loads analysis, and that's usually a gross design cycle input that permits the elements to essentially size their hardware and get that initial definition on the table. Design cycle 2 is where you get the detailed loads you roll in, the dynamics analysis, the coupled loads analysis, and get that final picture for the elements to move forward in their critical design review process. So it permits them to design the hardware in detail, as well as analyze it in detail to support CDR. And then after that, you move into the whole verification process. You move up that other side of the V into the verification, and the analysis after that is just to any loose ends that come out of the final design or final fabrication side. Cleanup of that, you roll in the final snapshot into the verification perspective. So that's typically how it's done. From an Ares 1X perspective, we stood up the quasi-static loads. Of course, the elements have already, we were dealing with heritage hardware, as well as there was initial concepts already on the table, so there was an initial sizing already on the table that a lot of the elements had already pushed forward with by the time we got the quasi-static loads on. So their quasi-static loads are conservative, and the measure against those, we had a lot of hardware that was designed to those levels, and but there were some areas that had to go back. They had to go back, and when they started getting into the more detailed analysis, they had to go back and tweak some of the areas. Upper stage had some areas that they had to do that with. But then there were other elements like first stage that were at a system level. We were dealing with a lot of churn from dealing with separation plane that caused a lot of involvement from the first stage side, and they were distracted from the normal design process. So when that occurred, they did not have time to go back, and when we went into the design cycle 2, getting all the detailed analysis down and in just wasn't happening and keeping up to speed. SE&I was trying to get the latest and greatest information on the table. From during design cycle 2, we were dealing with wind tunnel tests that were generating data that was supporting that coupled loads analysis, and there were some issues that popped up there that we had to go back and deal with. So we were constantly fighting, the issue side, and then trying to keep the tempo, the normal tempo that you would typically see in a design cycle process. It was just very compressed, and just the overlay of issues, and the fact that SC and I stood up late, and just trying to keep that tempo going was very difficult. We did have, on the first stage side, we did have some what we termed poke outs during design cycle 2 that actually bled over into design cycle 3. They weren't resolved in design cycle 2, and we were hoping design cycle 3 would get us out of the box, and or I should say in the box, but it didn't happen. So design cycle 3, we had to pull the cord on a Tiger team to get that resolved. So that's essentially the timeline and some of the reasoning why, given a typical project, what you go through, we were just dealing with a compressed time frame, as well as a lot of issues in there that didn't permit the design elements to do their normal in-depth work, get all of the analysis on the table to support CDR, and then the follow-on verification. It was just lagging. For day of launch loads, we eventually got everything within the box, and getting that final capability snapshot on the table for that we wanted to move forward into the day of launch loads effort. We agreed to that and got that on the table at the end game. And that, like I said, that's very important going into day of launch, and just the upper level wins and understanding those and rolling those back and doing the comparison with the trajectory folks to make sure we're still within the box is a key part. One of the areas that we had difficulty with was down in the Aft Skirt region, and just dealing with the heritage TVC system down there and the loads associated with that. And we had to really push hard on the load cycle 3 to get those resolved. It wasn't real evident what was driving the loads. When you're dealing with coupled loads analysis, there's a lot of what's affecting what, and the phasing of the loads during the flight and all that. All that has to be looked at from rollout, liftoff, ascent, and then recovery. Those all have to be looked at, and it's very difficult to get all that information on the table and look at it in one snapshot. If you're trying to do a quickly compressed design cycle and look at all those phases, which is essentially what we did. We did another iteration on design cycle 3, load cycle 3, as we called it, to see if we could get this problem fixed. We went back and scrubbed through all of the assumptions and inputs and models that went into design cycle 3. To see if there was anything in there that we were either missing or we could tweak and do better with. We looked at the Aft Skirt model. The Aft Skirt model was changed for design cycle 3, and we went back and scrubbed that in depth to make sure it was the right model to be using. We actually made a decision to go back to a more coarser model, as opposed to the one that was originally put on the table for design cycle 3. It was actually had more shuttle heritage behind it, and it was better understood by the analysts. We looked at all the mass properties to make sure all those were right. We looked at all of the forcing functions going into the model. We looked at the maneuver loads that were defined for flyaway. Those came in late. Also, realization of the whole flyaway maneuver was a late breaking aspect that had to be rolled in and understood. The question of whether, during ascent, whether flight maneuvers had to be rolled in, we looked at that. Also, there was an assumption way back that general conservatism in the STEL, the static aeroelastic loads, were put on the table that the maneuvers were essentially covered by that conservatism, and we went back and actually, voided that assumption and actually put in maneuver loads. So we went back and iterated on all of these perspectives to make sure we had the right picture on the table. That took a lot of time. It's load cycle 3. This is a post-delivery of load cycle 3 effort. So it was a Tiger team that was stood up after load cycle 3, between load cycle 3 and flight. So it was a very compressed time frame in order to make sure we were, pushing all the buttons we could to squeeze out, essentially sharpen our pencils on the whole analytical side. So in regards to the load cycle 3 and trying to, there's two ways to push on the rope. One is to have the elements go back and understand their capability down in their hardware and sharpen their pencil down at their level. And the other avenue is what I just described, us going up to the couple loads perspective and sharpening our pencils there. So you can go at it from two different perspectives. Obviously, going down and into the nuts and bolts analyses, there's hundreds, probably thousands of pages of analyses that have to be redone, and the time it takes to do that versus the time it takes for to tweak the analytical loads input side is you have to weigh each of those. As far as how we approached it, we did both perspectives. We actually ran the load cycle 3 again. I think we were at load cycle 3B by the time it was all done, and they took those and while we were generating those, they went back and understood where their capabilities were, where they had extra margin, and one of the efforts there is to understand. As you march through this design process, you typically have hardware that's designed to design cycle 1. It has a good margin. If it didn't meet design cycle 1, it had a negative margin, then obviously the elements would ask, well, let's do load cycle 2 and see if that fixes it. And so there's a back and forth that goes on there, either that or they dive back in and reanalyze to load cycle 2. So on the hardware side, as you march down the vehicle, you had some hardware that was designed to design cycle 1, some hardware was design cycle 2, and then some that didn't fit into design cycle 2 was had to line up on 3, otherwise you're out of luck. So and the game that you play there is margins, margins and the load conservatism. You have to go back in and understand all that, and that just takes a lot of time from the hardware perspective to have to continually go back and dig up the analyses, understand what load cycle that particular nut bolt component large piece of structure was designed to versus the margin that's there, and then try to line it back up with the margins that were or not the margins, but the load set that's going into flight. So there's a way to that is one of the mitigation steps that I feel should be chased on a future flight tests, is when you go into your planning up front, you make it clear to the elements that they need to keep that technical performance measure for all their hardware and essentially clearly delineate, this piece of hardware, design cycle 1 is good for it, and we're not going to change. This is the margin associated with it. So you constantly have that running, snapshot of, what the complete hardware is designed against. We struggled greatly at trying to put that together at the end game, and you eventually have to get there, especially when you're dealing with day of launch loads. You need to have that capability curve that you measure against and understand. But when the hardware's the hardware, if you're having difficulties with hardware, leading up to that point, it's nice to have the whole margin perspective and capability perspective on the table immediately, and not have to go try to dig. From a lessons learned perspective, there are two scenarios you can play out here. You can play out, if I can erase what we did and start over from a perfect systems engineering perspective, how would you formulate, if a given time and all that, how would you formulate to make sure everything happened? And the other perspective is to, given flight test, and flight test, typically brings a fast pace, high risk, a higher risk than a normal design development process typically takes on. How do you how do you still deal with that perspective, and what are some lessons learned that you could just overlay over top of that to help make that happen better? So going back to the former, which is the perfect world, obviously, the fundamental, thing is to stand SE&I up earlier. SE&I feeds all the elements. You shouldn't let contracts out before you have, system level requirements. Loads definition falls into the bucket of system level requirements that feed elements. So that typically would mean that, design cycle 1, you would want those quasi-static loads set on the table before, and in place before you let a contract and get people wound up in, sizing structure and so forth. So, that's the motherhood side of it. There's another aspect too of just the whole teaming to make sure everyone understands plans and how you approach, the integrated design and analysis. I think if we would have had the elements, participating at the SE&I level, sucked up some of the discipline level people out of the IPTs, as well as the lead systems engineers, to help put together, formulate, coagulate a plan for loads development that will get their buy-in. So if you do hit hardships down the road, they understand the pain that SE&I has to deal with to get that worked through. For instances, just models, sharing of models, and understanding, the inputs and assumptions, getting those laid out on the table, up front, from the IPTs, the integrated product design teams, get those laid out on the table and understood, all the ground rules and assumptions that SE&I puts into the analysis, making sure that not only models but inputs and assumptions are all documented properly and on the table, and you carry that forward, in the design process. That's the typical motherhood and apple pie thing. The configuration management aspect of all that is also very important. When you're doing quasi-static loads, the disciplinary guys, feel they have a little bit of looseness and, generating these conservative loads, but they're still making, assumptions and so forth, and you gotta sometimes bang them on the head to get that stuff written down and understood, and not just written down, but also configuration and controlled, so that, as you move forward, like I said in the process, that they adhere to, what they said and remember what they say, because when you're moving fast-paced, sometimes it's hard to remember. Your memory gets lost in the shuffle a lot of the times, and you have to have those reminders there to kick them into gear to feed the next design cycle. So that's the motherhood and apple pie perspective. Given the fast pace, I think of a typical flight test, the best thing to do is to make sure you document between each design cycle. You might not put that through configuration control, but maybe the responsibility needs to be more back on the lead systems engineer to grab that and make sure that it's posted on the wall as a scoreboard or whatever that everyone can look at, from not only SE&I perspective, but all of the elements, IPTs that have that visibility into it. The other aspect that I talked about earlier was the understanding the whole capability of the structure as you progress through the design cycles, and making sure that not only SE&I understands, but also each of the elements understands, what each piece of hardware is designed to, from a design cycle perspective, what they line up on, as well as the margin associated with that, so that if you do have hardware that you don't get to, that you don't have an opportunity to analyze until late in design cycle 2 or even after design cycle 2, there's a problem associated with that. You immediately have this broad picture that shows you essentially what a pseudo capability of the vehicle, what it is. at least what the design loads were and the margins were associated with that. It might not be a zero margin capability, but it gives you a measure. So that's I think, given those two perspectives, perfect world versus fast-paced flight test, I think those are the things that I would implement. The other aspect of loads development is the fact of the cross-disciplinary feeds required to inputs, if you want to call it that, into the loads that are from other disciplinary areas. Aero is an area that strongly feeds the coupled loads analysis, and that in order to develop some of those requires wind tunnel testing. Wind tunnel testing is something that you can't, it's not doing an analysis. There's a lot more that comes to the table and a lot more time required to accommodate a wind tunnel test. It's model development, it's instrumentation, getting the suite of instrumentation on there. It's actually getting the wind tunnel test time in there, and then also the thing that we struggle with is getting the reports out. So there's a strong timeline of things that have to be put in place to support that input. And if you don't have those stood up to feed the design cycles, loads design cycles, you can run into problems, and especially if you have issues. And we did have an issue on the rigid buffet model, and we actually had to stand up a Tiger team that went back and looked at that and actually adjusted some of the inputs that were put into the coupled loads analysis. So that did delay things between design cycle 2 and 3. And it was implemented actually late in design cycle 2, and we were feeling some of the effects in design cycle 3. So it is important to have those cross-disciplinary feeds understood up front and scheduled properly, so that that they need to be sucked forward as much as possible and forward fed from a resource standpoint. Really, even irregardless of whether it's a flight test or not, they need to just be stood up quickly and running way before the integrated design and analysis team gets their ducks in a row to support the elements. In regards to the element level participation at SE&I, I think I alluded to this when I talked about some of the lessons learned between the perfect world versus the fast-paced world. From a perfect world perspective, having the elements buy into what SE&I is planning, the design cycles, the needs for documenting models, constructs, models, assumptions, and inputs that they generate. All the IPTs are providing, essentially their element models, and they are rolled up into an integrated system level model. And we do some level of goodness checks, but really the responsibility in making sure that those submodels actually represent the design, that responsibility is on the IPTs to make sure that happens. So making sure that they understand the planning and of the integrated design and analysis cycle, and making sure that they document and provide that information along with their models, document and review their models. They need to have some level of goodness reviews on their side. They can't just you can't just take a guy sitting at his desk shouldn't just email the model to the system level guy. There should be okay, that subsystem guy should say, okay, I'm done with this model. Here's everything associated with it, all the inputs, all the assumptions and everything associated with it, and their organization should review that, and then dump that over the fence to SE&I when they're okay with it. And then we integrate and do our goodness checks to make sure there's nothing funny going on, and then we run it. So having an understanding of that whole path and making sure that IPTs follow that in a fast-paced environment is something that's critical to making things happen fast. And there again, when you do run into problems down the road, you have all that on the table and can fall back on that and understand specifically what they provided and so forth. So getting them integrated into the planning up front and getting them to buy into providing all that information and understanding what deliverables they need to make and what that deliverable needs to be consist of, I think is a tremendous value added to have that done up front before that planning and process agreed to up front before they begin running. So